anything down right now, okay? If you want to, if you guys like the derivation, if you like to know where it came from, stuff like that, you can write that in there. But the actual law of cosines we'll get at the end, just like we got the actual law of sine. Okay? So here is triangle ABC. Okay? And just like last time we discussed, it's often important for us to draw in, that's not going to work, this height that we may need in order to find or measure some other things. Okay? And then I'm going to name the sides across from the angles of the triangle using the lowercase letter that they are opposite from. So here's angle C. Across from that would be side length C, side length A, and then this whole thing here would be side length B. Okay? This D right here is just so that when we're talking about triangles, we can name them and know which one we're talking about. Okay? So when we were doing the law of sines, we focused on area, and area really built that relationship, and that was focused a lot on finding the height. Okay? The relationship we're going to build with cosine is not going to focus on finding the height necessarily. It's going to focus on these two small triangles again, but also the length of this side once it's been split by this point D. Okay? So let's say that I call this portion of it X, because I don't know where it's getting split. Then what could I call this other portion from D to C? Good, B minus X. The whole length B minus the portion that I've called X is what's left for over here. Okay? And again, our goal is to build something that doesn't really use the X's or the H's, that just revolves around A's and B's and C's. Okay? So if we look at triangle ABD, so this right triangle that's on the left side. Sorry, Monet, yes? You're good? Okay. So if we look at triangle ABD, the triangle that's on the left side, there are a couple things we know about this triangle. Okay? One thing is we could relate all these side lengths using the Pythagorean theorem. Right? So we could say like x squared plus h squared equals c squared. Is that okay with everybody? Okay. We could do the same thing with the right triangle that's now on the right side of the diagram, triangle BCD. We could say b minus x squared plus h squared equals a squared. Okay? And just like with when we were looking at the law of sines, if we had drawn this height in a different position, then instead of using A and C how they are now, we might be using B and C or A and B, all dependent on where we draw in that altitude. Okay? All right, now something else that can relate H and X together, because that's not going to be enough, or can at least relate X to A, B, or C. Just like we did before, we can take an angle, and since trigonometry of right triangles lets us relate the angle measurements to the side lengths, we can write a trig equation using that angle and two of the sides. Okay, so here I'm going to choose, and I'm choosing this because of what I know I'm trying to figure out, that I'm going to choose that the cosine, I'm going to use cosine this time, because then that's going to give me something about x. Okay? So the cosine of angle A equals adjacent over hypotenuse, or in that triangle, x over c. And that means that anywhere I see an x in my problem, I can replace it with c times, I don't know why it's weird, sorry, the cosine of A. Okay. Having some trouble in that area. All right, so c times the cosine of A is what x is going to equal. That's going to be useful to me because, remember, I don't want formulas that contain h and x. What I want in order for it to be useful to me is formulas that contain A, B's, and C's, either angles or side lengths, because that means I don't have to find any extra information on my triangle that's not right. I can just use the lengths that are given to me. Okay? So now how to put all this stuff together so that we do just have a formula with A's, B's, and C's in it. So the first thing is we can do some sort of system with these two equations here, trying to simplify them so that there aren't as many x's and h's present. So the way I'm going to try and get rid of one of the variables is I'm going to take this and solve it for h squared. So h squared equals c squared minus x squared. And now I'm going to go plug that in here. Okay, so I'm treating this like a system of equations, like I'm trying to solve it. There's so many variables I can't really get a solution from that one single system, but I can at least rewrite stuff so that it has less variables. Because now if I rewrite this equation I can replace h squared with c minus x squared. And even though I'm putting a c in that equation, remember my goal is to get stuff in terms of a's and b's and c's. So getting to remove the h and replace it with x, which is already in this equation, and something that has to do with a, b, or c is a step in the right direction because at least I'm getting towards stuff that just has a, b, and c. Okay? So I'm going to multiply out this. Okay? So that's going to be b squared minus 2bx plus x squared. Then I'm going to replace h squared with what it's equal to. So according to this equation, h squared is equal to c squared minus x squared. So plus c squared minus x squared. Again, that came because I replaced h with what it was equal to. Now notice that this helps get us really close to having something that's just dependent on a, b, or c, because x is the only thing here that's kind of hindering me being at the finished point. And the positive x squared and the negative x squared cancel out. So what I have currently is b squared minus 2bx plus c squared is equal to a squared. So now if I can just get rid of the x and have it in terms of a or b or c, then I'm done and I have a formula that I can use with the original given triangle that doesn't need me to draw in the altitude and find the heights or anything like that. Okay? So this is why over here I chose to use the cosine, because I really wanted to write an equation that just revolved around x and related x back to a's, b's, and c's. And notice we came up with that x is equal to c times the cosine of a. So I'm going to go to this equation, and I'm going to replace x with what that equation said. So it said x was equal to c times the cosine of angle A. Okay, now we're going to rearrange it a little bit, but this is basically the law of cosines. So the law of sines is a pretty looking formula, but it's heavy, right? There's a lot that goes with it. You can't just jump right in and use the law of sines, right? You got to do all this analysis at the beginning. Is there really a triangle? Is there just one? Are there two triangles? Okay. The law of cosines is not so pretty looking, right? It's ugly, but there are some patterns we can catch on to that are happening here, okay? With a little rearranging, we'll be able to see that. It's ugly, okay? But the good news is, look at what you use. You find a third side of the triangle, okay? So you would use this to find A. And in order to find A, you would have to be able to plug in values for B and C and angle A. Where is angle A with respect to B and C side lengths? In the middle of them. So what this is really telling me is I can find this side over here if I have a side, another side, and the angle that's in between them. Does that make sense? So the cool thing about this is if you do have a side, an angle, and another side, do you for sure have one triangle? So if I made you all draw on your paper a side of a certain length and connect a side of another certain length to it with a specific angle between them, would you for sure be able to finish then building that triangle on your own? And would we all build the same triangle? Yeah, so there's exactly one triangle that exists here. It can't be any different. This is part of the reason why the side angle side postulate worked in geometry. Because if someone had this side length with this angle and this side length, there's only one other way that these could be connected to be done, right? Because they're set lengths. You don't get to choose a third length. So we would all have to draw in that third side that just connected those other two endpoints, and we would all be forced to have the same triangle. So if you really do have that side angle side group of information in which you would use the law of cosines, you have exactly one triangle for sure because of that geometry principle. Okay? So, bad thing about the law of sines, ugly formula, right? Look at it. Ugly, right? Law of sines, oh, so simple. Sine A over A, sine B over B, right? Very nice formula. Law of cosines, not a lot of critical thinking or analysis at the beginning, because if I do have this group of information, I for sure have one set triangle. Law of sines, that angle side group of information, difficult to deal with and analyze at the beginning. So it's like a trade-off, okay? Ugly formula for less analysis at the beginning. All right, so let's write down what our formulas look like. And we're going to rearrange them a little bit to help you see some patterns. So the formula we came up with said A squared is equal to B squared plus C squared. I'm going to put that part at the beginning. I like it because it kind of looks like the Pythagorean theorem, okay? Like something squared equals something squared plus something else squared. But then we had something being subtracted from them, okay? And the part that you subtract had a 2 with it, right? Okay. Then it was two things multiplied together. These two same side lengths that you were using over here. So it was B and C. And then it is the law of cosines. So it has a cosine in it. And the cosine of the angle you're using is the angle between these two sides you're using, which means it's not angle B or angle C because it's touching them and between them. So the angle actually matches the side over here. Okay? So there's actually, just like in the law of sines, there's 3 different versions of how we can write this formula, because it doesn't really have to always be that you're specifically finding side A. It's basically saying if you have any 2 sides and the angle between them, you can find the third side using this pattern of operations right here. Okay? Minchao? Yes. Okay. So here, if I was finding B squared, what do you think the formula is going to look like based on the pattern that we just talked about? What are the 2 sides I'm going to use to find B? Monet? Okay, so here they're going to be added, but it's going to be an A squared and a C squared. Okay? I'm still going to subtract something at the end with a 2. And I'm going to keep using these 2 side lengths I was using. So it's still going to have A and C, okay, times the cosine of some angle. In this case, which angle would I be using? B. Okay? The angle that you use is always across from this side that's over here by itself that you're trying to find. Okay? Or it's in between these 2 side lengths here. So this would be a B. All right, so of course there's a third version of this formula. Okay? It says that to find C squared, what 2 side lengths would you use? A squared and B squared. Okay, so then we'd subtract 2 times the same 2 sides we've been using, and the cosine of an angle, which in this case would be C. Okay. It's really the same formula, and do they have to name their triangle ABC? No, they could call it triangle XYZ. So the important part to remember here is basically over here on this side of the formula. No, it's like something squared plus something else squared minus 2 times those same 2 sides and the cosine of the angle between them. Therefore, not the same 2 letters that you've used over here. Okay? Yeah, Jenny?
Okay.
No, not.
You're given 2 sides of the angle, but what about the time you 2 sides of the angle given is in between?
Good. So that's a law of sines problem because then it would be an angle side setup.
Okay.
All right? So what Jenny said is exactly the point we're trying to get to. She said, okay, you said we can use this if we know this information here and this one here and this one here. We can find this third one over here. What if they don't give me this, this, and this? What if they don't give me this side and they give me this side? This is where we'd want to use the law of sines, right? Because then we have the angle and the side across from it to set up that ratio that we're looking for. But then that problem requires me to do more analysis before I start it. Because just because they give me an angle, a side, and another side length, does that for sure guarantee you could build a triangle? No, you might not be able to build one at all. You might be able to build exactly one, or you might actually be able to build 2, right? Like depending on the side lengths, maybe this guy can fit right here, and he could also fit right there. Okay? So whenever you go to use the law of sines, because you have that group of information, you need to do more work up front. Okay, and analyze how many triangles there are and then go find your stuff. If you have the side angle side and you're starting right away with law of cosines, you're golden. You have one triangle, you know for sure, and now you can use any tools to figure out what you need to figure out. Matt?
So wait, for law of sines,
Mm-hmm.
if you only have one triangle, then that triangle is right.
Well, maybe not, but I know. We'll look at it more closely. We'll see how sometimes. We're just basically guaranteeing there's only one way that height can fit, but the way we put it together doesn't necessarily have to be right. The proof of it is showing the shortest distance in that case, but we can use this without right triangles, and sometimes there are one. Like, if you only have one triangle, side A could just be bigger than side B. Like, there could just be that obtuse angle in there, and that doesn't mean that it's right. It means because remember, at first you looked at the angle sizes, right, and the side lengths. And only in that third situation, then you had a right triangle. So it's not every time there's one triangle, it's a right triangle. There are some special cases where it'll end up being that way. Okay? All right. So basically your quiz on Friday is going to be pretty short. Those of you that haven't presented yet, you'll present on Friday, okay, after the quiz, because it won't be that long. And it's just going to be a couple of different questions. Either you're going to have a right triangle you have to solve, and then you can use like flat out trig stuff, right? Or you're going to have a triangle that's not a right triangle, and then you're going to have to navigate through the law of sines and law of cosines to figure out what you need to figure out, okay? So here's an example. It says find C if A equals 15, B equals 18, and C equals 34 degrees. Now, I could draw a picture, but do I know for sure by the given information that I've been given two sides of the triangle and the angle in between them? Based on the letters, yes, okay? Because they didn't give me side C, so they had to have given me the other two sides of the triangles that are not across from angle C, which means they must be surrounding angle C, okay?
Like a general question.
Mhm.
Are there, for the law of cosines, are there still going to be like the cases, like
No.
law of sines, like the 0, 1, and 2 solution?
No.
Okay.
Because law of sines only benefits us in situations like this.
Okay.
And if you have the two sides and the angle between them, there's only that definite one way to build the triangle, so there's one length that we're looking for to complete it, okay? So either you knew right away by the given information, or you didn't, and you drew a triangle and you called it triangle ABC. But then as you fill in the given information, you're supposed to find C. If you know this is 34 degrees, this is 18, and this is 15. And you can see that you have that side angle side scenario, which you know there is exactly one triangle then built. The law of sines wouldn't work here because if I tried to set up a ratio, the only angle I have is the 34-degree angle, and I don't have the side across from it. So that would be a good hint for me to go and try to use the law of cosines. Okay? And the law of cosines finds a side using the angle across from it and the two sides that are along that. Okay? So in this case, c squared is equal to, remember, the two sides surrounding the angle being added together and squared. So 15 squared plus 18 squared. Minus 2 times each of the side lengths that we used previously times the cosine of the angle between them. Now, that's me having memorized the formula, and that's the part you're going to have to do, right? No one else can do that for you. Okay. Yeah, and so then we'll do this on our calculator. Make sure your calculator is in degree mode. Which one? Which one is it? Oh, 5. Thank you. Oh, but that seems... Oh, that's the squared part, right? Take the square root of it for me.
It's 22.9.
Still seems a little bit big. Okay. Okay. So let's look at how we're typing this in. So you should be able... Yeah, I think 22.9 is a little bit off just because it's across from a 34-degree angle. So one of these angles probably has to be bigger than that. And they're across from 15 and 18, so I would expect it to be smaller than at least one of those. So 15 squared plus 18 squared minus 2 is 15 times 18 cosine 34. Yeah, so I got 10.1. Eric? So before I took the square root, I had like 101.3. So try entering it again, and then if by the end of the lesson your answers aren't coming out the same as ours, I'll look individually at how you're entering them into the calculator, and we'll try and fix that. Okay? So is this okay with everybody, how like there could be a straightforward question, and then this would lead you to use law of cosines given this system of information? Okay? And then the questions, are we okay with going for them? The questions like we would see on the quiz are just going to say to solve a triangle. Okay? So here we have some information. I'm going to draw a picture. I don't really know what's happening yet, so I'll see. So what are you going to use to start this problem? We have to find everything. So we have to find two angles and a side, but we have to have a starting place. So it's not for sure a right triangle, so we can't just start with regular trig equations. So then your choices are law of sines and law of cosines. And which one would you start with in this situation? Cosines. And if you're having a hard time identifying, like, how do I know if it's law of cosines, just try to decide if it's not law of sines, right? For law of sines, you need an angle and the side across from it to set up your little ratio. If you can't set up one of those ratios, you need to try something different than the law of sines, which would be the law of cosines. Okay? So I'm going to work on using the law of cosines first to find that side over there, because that's one thing that it will find me. Okay, so find for me. I'm going to use the 22 and the 27 as my two side lengths in the formula, and the cosine of 47. So we'll put the calculation in the calculator. Did you take the square root of it? Yeah, so before you take the square root, you get it like 402.8. But then if we take the square root, we get 20.1. And that looks more in realm with our numbers that are around our triangle, right? Okay. So I get here 20.1. I was allowed to immediately start this problem because I know there's one triangle based again on that idea of they gave me a side, an angle, and a side. There is one specific side length that will for sure complete this triangle. I have to just go find what it is, right? So that's what I did. So I already knew there was one triangle. So now I've done this. How am I going to find angle B and angle C? Good. So you could go through now and you could do the law of cosines, but it's kind of a pain in the butt to solve for the angle. The law of sines is a much simpler equation to solve. So once you know for sure how many triangles you have and that it is a solvable problem, and so we knew right away this is one triangle and we went and found one piece. Now that we have an angle and the side across from it, we can use our law of sines to help us get through the rest. And we don't even have to do the analysis part because we already know from the given information at the beginning there is one exact triangle, and then we're going to go ahead and finish solving it. Okay? The only thing we need to be a little bit aware of is the order in which we go find the angles. So make a note on this about this on your paper. If you are solving for an angle using the law of sines, okay? So let's say I set this up. I'm going to do the sine of 47 over 20.1 equals, and I actually feel like I have two choices right now, right? I can do the sine of angle B over 22 or the sine of angle C over 27, but there is actually one of these angles that I should solve for before I go looking for the other. Do you guys know anything about angle B compared to angle C? Just knowing the sides that they're across from. Minchao? Good. Angle C is bigger than angle B. Okay? I want you guys to take your calculator right now, and to solve this problem, we're going to be looking for an angle, either angle B or angle C, right? Trying to make the point of which one we're going to look for first right now. I want you guys to take your calculator. This means the last step we're going to do in the problem in our calculator is we're going to do the inverse sine of something, okay? So the first thing I'm going to tell you, and we'll talk more about why later, is that you cannot take the inverse sine of something bigger than 1. Anybody have any idea why? What is the sine ratio? How do you build a sine ratio in a triangle? You do what? Opposite over hypotenuse. So this is supposed to be the ratio in here, and you're taking the inverse sine of it to find an angle. If in here is supposed to be opposite side divided by a hypotenuse, what's the biggest part of the triangle? Hypotenuse. If this is bigger than 1, that meant the opposite was bigger than the hypotenuse. Is that possible? No. So first of all, you can't take the inverse sine of anything more than 1. So go ahead and pick a number less than 1, not a negative, so just do something like, I don't know, 0.3 or whatever you want. But in your calculator, do the inverse sine of something. I don't care what. Did anybody get an answer over 90? So you all typed in whatever you wanted, but nobody got an answer over 90. That's because, and again, we'll talk more about this later, when we do the inverse function, it's restricted to choose things between negative 90 and positive 90, and we'll talk about what that is. That means if there's an angle bigger than 90 in my triangle, is my calculator going to come up with that answer? No. So which angle should I look for first? The one across from the 22 or the one across from the 27? Which one, if this triangle does have an obtuse angle, which angle is it going to be? C. So which one should I look for first if I know for sure my calculator will not identify obtuse angles? B. Okay? So when finding missing angles using the law of sines, when you have one angle and you're looking for some other ones, start with the one you know is smaller, okay? For the reason that I just told you about the calculator, okay? And we'll see a lot more different connections later about why that works. So you're going to cross multiply this, and then you're going to solve. I'm just going to tell you guys what the answer is, just for time's sake. Should get 53. Rounded to the nearest degree, that would be 53. And so then to find angle C, I'll just add those up and subtract from 180. So we have 100 degrees so far in our triangle. This is 80. So we actually could have found angle C, and it would have been fine. And what could you do to know if there was an obtuse angle in this triangle or not? Do you guys remember from geometry?
You do a squared plus b squared, and this is 3
Good. You take the two smaller sides of the triangle and do a squared plus b squared or whatever. Okay? But c squared in this case doesn't necessarily mean the letter c. It means like the longest side of the triangle. But if you take the two smaller sides, like you're using the Pythagorean theorem or something, remember a squared plus b squared. And then separately calculate the longer side squared. Okay? And then when you compare them, you'll be able to see. If they're equal, you have a right triangle. That's what the Pythagorean theorem says. Right? If they're not equal, if these two added together are bigger than the one squared by itself, then it's acute. But if the one squared by itself is larger than even the other two squares added together, it's obtuse. I'm not saying you have to do that. Okay? If you don't want to do that analysis every time, your best bet is to look for an angle you know will be an acute angle first. Then you don't have to worry about any of that. And then it will lend itself to finding the obtuse angle later if they add up to something less than, 9. Okay? Are we okay with this? So law of cosines, not as much analysis, but you got to memorize a few formulas. Okay? So when you come in tomorrow, I'm going to have 3 problems up on the board with worked out solutions step by step taped up there as extra practice of this concept. Otherwise, you guys are going to be using the period to work on homework. So if you want to take pictures of your textbook or whatever the case may be, we have some in here, but not a lot. And that's homework problems from homeworks 1, 2, or 3. Okay? Does everybody understand? Yes?